Okay. We are recording. I think I am. Reese, can you hear me?
Yeah, I can hear you.
Okay, good. Everything's working then. All right, we're good to go. I got a textbook in front of me. I'm actually going to try to pop open the exam too, so I actually have it on screen. What's your first question, Isabel?
Well,
Just tell me.
any questions.
Just tell me what page it's on. I'll open up the. I should be able to get to the exam pretty quick.
Oh, okay. So page 2, the first one.
All right, page 2. That is the Gabriel synthesis. It's got A and then B. That the one you're talking about?
No, the top one.
Hmm?
What do you mean A and B?
The first reaction goes to compound A, and then compound A goes to compound B. Is that what we're looking at?
No.
Second page of the exam?
Oh, third page. Sorry.
Third page. Okay. That's completely different. Okay, this is, yeah.
I'm sorry.
You said page 2. I went to page 2.
Well,
You know?
please start reading my
I took you at your word.
Well, maybe we should have.
All right, so we've got, what do we got? O minus CH3. O. And where's that in O2 group? Adjacent right here. We got that. I'm looking for mechanism. So we're looking for the mechanism of the reaction, and then we're looking for why this thing happens in the first place. Oops, SO2 minus, not SO3 minus. All right. Okay. So the first thing to do is try to figure out which carbon is which. Right, so we know where the reaction is taking place. So let's start numbering where the nitrogen is. And number that ring like that. Obviously this is carbon 1. Probably this is carbon 2, because that's attached to oxygen. And this oxygen is fairly clearly this oxygen, because it's the one that's opposite the methyl group. So if we wanted to number this ring, we would number it using primes. Right, so pretty clearly 1' is still the one that's attached, 2' is still attached to the sulfur. So that helps us identify where the reaction is taking place. And what we're doing is we're changing the identity of the oxygen that's attached to carbon 2. Right? So carbon 2 is where the substitution is going on, which means this is an ipso substitution. We've got a phenoxide ion, and we've got a nitro group in the 2 position, which is usually favorable for ipso substitution. So we can attack this carbon with that pair of electrons, and we will be able to migrate this bond all the way around so that it's on the oxygen, which makes it most stable. So both of these oxygens are now going to simultaneously be attached to carbon-2. And we are going to have bonds look like this. So if I want to number these, right, this is the 1' here. 2' is where the substitution is going on, or sorry, 1, 2, 3, 4, 5, 6. And then over here we've got 1'. 2', that's a sulfur, not an oxygen. So there's the intermediate that has broken the aromaticity, put an sp3 hybridized carbon in there. Which means that it's going to want to reestablish aromaticity, and it can do that by having this pair of electrons come back in, move the electrons back around the ring, and kick out this leaving group to give the product. So it's just a two-step mechanism. Attack at carbon-2 with the phenoxide ion, and then kick out the leaving group. To understand why it's favorable, we should actually draw the full Lewis structure for that group, which looks like that. And we realize that this is resonance stabilized, whereas the product is not, or the starting material is not. So because the product has those two resonance forms that spread the charge out over the two negatively charged oxygens, whereas this is just a single one, right? That's more stable. Basically what you're doing is you're comparing the acidity of a phenol, which without the SO3 group, right? If it's just a phenol and that sulfur is not there deactivating the ring, the pKa would be around 10-ish. And you're comparing that with the pKa of basically sulfurous acid, which is significantly less than 10. So it's much more acidic. I don't actually remember what the pKa of sulfurous acid is, but I think it's on the order of 2, something like that. H2SO3. Question mark, you could look that up in the Gen Chem text if you wanted to know exactly, but the resonance stabilization is the reason it's a better acid. You can have resonance stabilization here, but not without breaking the aromaticity of the ring, right? You can distribute that charge onto carbon-6, carbon-3', onto carbon-2', 4', and 6'. But then you have to break the aromaticity of the ring, whereas you have two resonance structures here, neither of which breaks the aromaticity of the ring. More stable anion, ipso substitution. And that is problem, where is it? Pretty sure I took that out of the textbook. Don't remember where in the textbook, but I think I took it out of the textbook. Maybe I took it out of a different textbook. Yeah, it's exercise 22.9 on page 1060. there it says hint. This is a nucleophilic aromatic substitution. I figured you didn't need the hint.
I really didn't know where to start, so.
Numbering carbons is usually a way to start, so you can figure out where the reaction is taking place. Right, the nitro group isn't going anywhere. The methyl group isn't going anywhere, so those are kind of your anchors, and then you can number the rings accordingly. Once you recognize that this oxygen is attached to the same carbon that that oxygen used to be attached to, then it becomes fairly obvious that it was an ipso substitution. The nitro group is also kind of a tip-off. When you have a negatively charged nucleophile and you have a nitro group present, ipso is common. So it's different from the ones we showed in class because in this case the leaving group isn't a halide. The leaving group is this sulfurous acid derivative, basically sulfate, sulfonite ion. On the exam, that was supposed to be the second time you'd seen it, though, because it was exercise 22. You do all the chapter exercises, right?
Like the problems?
Hmm?
Like, is that the problems, like problem sets?
Yeah, but you do all the chapter exercises when you do the reading, right?
No.
Oh, that's unfortunate. Because that's where that problem came from. Doesn't it say in my syllabus that the chapter exercises are considered part of the reading assignment? I'm pretty sure it says that if you read the fine print. There's always fine print. All right, next.
Am I allowed to ask another one?
Well, anybody who chimes in first.
Okay, can you do number, like the second one?
Page 4.
The second one?
Actual page 4.
Actual page 4.
Not page 5.
Huh?
Not page 5, 4.
Oh,
The actual page 4.
what I tried doing was like, I don't know.
So what it's saying is it has a large dipole moment comparable to that of HF.
Yeah.
And we know that HF should be pretty polar because that has a difference in electronegativity of 1.9. Which is right on the border of being considered an ionic bond. It's not an ionic bond because they're both really small atoms, so you get really good orbital overlap. But we've got a really large charge separation. So what that's telling you is this also has a really large charge separation, right? Dipole moment comparable to that of HF. Explain.
I think, never mind, I see what I did.
And that is also a problem from the book. I can't remember if it's from the exercises or the end of the chapter. I think this one's from the end of the chapter. Maybe. Yeah, I'll go look for it later. So what you have to notice is you have to notice that if this were a negative charge here, if you did this, and wrote the resonance
So
structure.
I did that, but I did it for both, because I was like, oh, it's 4 pi electron, because that's not.
So if you do that, this is a 6 pi electron system, which is 4n plus 2, n equals 1. And this is a 2 pi electron system, which is 4n plus 2, n equals 0. So both of these two rings are aromatic.
So we can use n equals 0 as a,
Oh yeah, n equals 0 is legit.
okay.
So cyclopropenyl cation is aromatic. Both of these are aromatic. So then you could draw the orbital energy diagrams for both of those. Did it ask for that?
No?
Did it imply that you should have them? Well, it's worth 8 points. If you wanted all 8 points of that, the energy diagrams would have been a really good plan. All right, so there's a closed shell for that one. And then the other one is also a closed shell. Both of them have all the bonding orbitals filled and all the anti-bonding orbitals empty. As you'll see in the one that has 5 orbitals, these are the 2 bonding orbitals are closer to the p orbital energy level than the anti-bonding because there are 3 down and 2 up. Whereas in the other case, the pi 1 is lower, further below than pi 2 star and pi 3 star are above because there's 1 down and 2 up. And the sum of the energies has to add up. So you can have 2 closed shell systems by writing this. So normally you would think, but this is charge separation, right? That's a minor resonance structure, but in fact, what this is telling you is that that charge separated resonance structure is actually the major resonance form, the most important resonance contributor, and that one has a complete full charge separation. Kind of like HF, which has almost a complete full charge separation. Can't remember what it is for HF. It's like plus 0.4 and negative 0.4 maybe-ish. Might be more than that even. It's significantly ionic. So that was an aromaticity question.
Works a lot better with only 2 electrons instead of 4.
It does not have 4 electrons, yes, because there's no lone pair there. If you split this up and put 2 electrons that way and 2 electrons that way, then you just made a dianion.
Yeah,
And that's no good.
it's not good.
There are some dianions that are aromatic. The cyclooctatetraenol dianion is aromatic, but that's not one of them.
So I remember like just a random thing, like for the like we can use the circle, but for the one above it, because it's 2 things together, I think like I used the circle thing to figure out where the orbitals were, and that worked.
Oh, the inscribing it in a circle thing?
Yeah.
It works for each ring separately. It doesn't work for bicyclic structures,
Okay, because I think I got it to work for this bicyclic one.
but it would work for this, for that one, and it would work for this one.
I meant the bicyclic above it, like the first question on the page.
Oh, the first one? Yeah, it might work for that one.
Like, if it doesn't, what's a better way to figure that out? Because it's only 8 points and having a long time drawing all these things.
So which one were you looking at? You were looking at the parent compound?
Like, it doesn't matter necessarily. Like, we're just trying to figure out where like how many orbitals there are. Because when you count your carbons, you have 8. But then there are 9 things. Wait, no, I think there's only 8. But just like the arrangement of them.
So there are 8 p orbitals.
Yeah.
These are 8 pi orbitals.
Uh-huh.
And that's an even number, which means that there's always going to be 1 low, and then pairs, and in this case, 1 up.
Yeah.
In this case, because there are 3 sets of pairs, pi 4 and pi 5 are actually non-bonding orbitals. At the original p orbital energy level, 6, 7, and 8 are the anti-bonding, and there's 8 electrons in there, 1, 2, 3, 4, 5, 6, 7, 8. So this is an open shell. And it's 4 n pi electrons, and n equals 2. So that's an anti-aromatic compound, the parent. The dianion is an aromatic compound because when you make the dianion, you just filled those orbitals. So now you have a closed shell.
I was just saying, like, when you inscribe, if you were to inscribe that in a circle with one of those things at the bottom, I think that helped, like, that worked.
That one actually does work, but it's not generally true. It happens to work because there are an odd number of carbons in this ring. If there weren't an odd number of carbons in that ring, it wouldn't work. It wouldn't work for this system, right?
Well, obviously.
think your first mistake was using the word obviously. It's not necessarily obvious, but yeah, it doesn't work. Because you have to have you always have to have one unpaired at the bottom. There's only one way to put everything in phase. So that one is a case where it'll actually react with potassium. Potassium will just give up 2 electrons so that it can close its shell and have a completely aromatic. It's still a 8-carbon system. Right? There's 8 atoms in the ring, but there's 10 electrons in the pi system. And it's the number of electrons in the pi system that matters for aromaticity, not the number of atoms. Yeah, compound C is incredibly unstable. Compound A, of course, is non-aromatic. Compound A on that thing has 2 sp3 hybridized carbons in it. So it's neither aromatic nor... It does have 6 pi electrons, but that's irrelevant because it's not a cyclic pi system. You've got to be a cyclic pi system first before we start worrying about whether you're aromatic or not. That top one is exercise 1519 on page 692. And I swear I got the other one from chapter 2. Yeah. Page 8. Actual page 8 or the 8th page of the exam? Page 8 of 10. Okay, the actual page 8.
So, you know how to explain the orbital energy diagrams? Because I'm just thinking it would, that's because of the diesel localized systems. Or is that because of the time orbital class?
Okay, so the question asks you to explain in detail the seemingly contradictory observations that while the stability of a conjugated pi system increases with length of system, so does the reactivity. So what we want to do is we want to compare the orbital energy diagram for a shorter system to the orbital energy diagram for a longer system. The logical thing to do in that situation would be to compare just ethene to one 3-butadiene to the hexadiene. Or if you want, right, just ethene versus that versus. So what we want to explain is why that's more stable than this, and this is more stable than that, but this is also more reactive. No, because we want to use a molecular orbital diagram, a molecular orbital argument for this.
And by that, you just mean like energy diagram, right? Or do you want us to draw all of the things?
It didn't say sketch the orbitals, and
Okay.
usually if it wants you to sketch the orbitals, it will ask you to sketch the orbitals.
Okay, cool.
Right, but it does say orbital energy diagrams would be a good idea. So it's effectively asking you to compare the orbital energy diagrams for these 3 systems. So we start with just this plain old pi and pi star orbitals, where that one's filled. And then we go to the 4 pi system, and we realize that pi 1 is now going to be lower in energy. Pi 2 is going to be here, and we want to try to make these about the same distance apart. And what you'll see is that the distance between pi 1 and pi 4 star doesn't double. The number of orbitals doubles, but the total energy gap from top to bottom orbital doesn't double. So the result is that it squeezes the orbitals closer together. And then we go to the 6 pi system, and we're going to drop this orbital some more. There's going to be pi 2. There's going to be pi 3. Pi 4 star. Pi 5 star. Pi 6 star. And I may or may not have done a very good job of putting them approximately the same distance apart. So the stability is determined primarily by that low energy orbital. These 2 electrons are quite a bit happier in the 3 double bond system than they are in the 2 double bond system, and those are happier than just the single double bond system, so that increases the stability of the system. But the HOMO is the orbital that dictates the reactivity. And the longer the pi system, the closer that HOMO gets to the original p orbital energy level. So these are higher energy electrons than those, and these are higher energy electrons than those. So when you want to react, right, that's what matters. When you want to talk about stability, these 2 electrons are pretty happy too, right? These 4 electrons are all happier than these 4 were. Those are less happy, and those are the ones that are reacting. But 4 electrons are really happy in the lower energy orbitals. The crux of the thing is that as the number of orbitals increases, the distance from the top to the bottom energy orbital doesn't increase fast enough to keep pace. If it did, right, if it doubled, then pi 2 would be at the same place as pi here, and there'd be no change in reactivity. So if you were a nucleophile trying to attack that pi system, that's a lower energy orbital, put electrons in. But pi systems in general act as nucleophiles, not as electrophiles. You do electrophilic addition reactions to these. Nucleophiles generally won't attack a carbon-carbon double bond. These are electron-rich species. So the HOMO is the orbital that really matters. And if you just take a generic electrophile and attack it, you can also look at the intermediate. Right? The intermediate for this one is a primary carbocation. Well, that's not so good. The intermediate for this one is allylic. So it's resonance stabilized. And the intermediate for this one is doubly allylic. Oops. Added a carbon I didn't mean to add. So there's actually 3 resonance structures for this structure and 2 resonance structures for that, and only the 1 structure for that one. So if you wanted to, you could draw the energy diagrams for the intermediates, and you could show that the allylic system looks like this. Pi 2 is non-bonding. Pi 3 is the anti-bonding orbital. And then for the 5-carbon system, you've still got a non-bonding orbital, pi 3. Right, so you could show that this pi system, this 5-orbital system, is more stable than the 3-orbital system because pi 1 drops for that as well. So better to show it like this. Basically, the difference between the orbital that dictates the stability, which is the most stable one, and the one that dictates the reactivity, which is the highest energy occupied orbital. But you were saying resonance, right? So this is the resonance argument for the same thing. The resonance would have gotten you a fair number of the points, but it did say orbital energy diagrams would be a good idea, and that translates as draw the orbital energy diagrams. So it seems odd, right? It seems like if it's more stable, it should be less reactive, but it's not, because different orbitals are dictating those 2 things. And you could have gotten, I mean, if you felt really ambitious, you could have drawn the 8 pi system and the 10 pi system and just used up all the paper.
Would you have been satisfied with only 2?
As long as they were these 2, with these 2, yeah, it's a little sketch. Because then, if you're comparing these 2, then you're not implicitly comparing these, and that's what I wanted you to notice, that this cation is more stable than that one. Sorry, the other way around. Right, this carbon cation is stable in that one. A really complete answer would have included these as well, but I probably would have given you the points for just that. It's all relative. It's a 10-point question though, so, right, you got to do 10 points worth of work.
That's 10 points right there.
Right here, 10 points worth on the board. The resonance argument wasn't necessary at all. You could have left that out. Yeah, I would have given full credit for this diagram and the sentences that explain that the lowest energy orbital drops every time you extend the system by another double bond. The lowest energy orbital drops, but the HOMO rises. Those are the sentences I would have wanted. And I think I showed the 8-pi system as well, and either in class or the pre-recorded video is one of those. In the limit of infinite length, if you have an infinitely long system, then you just have a band of orbitals where there's basically no energy gap between them, which is very similar to what you have for metals. If you remember from general chemistry, right, for metals you had a band, like you had the 3s band and then you had the 3p band. Right, and when the 3s and the 3p bands kind of overlap, that's when you can get some conductivity, because now these electrons can raise into that level and these electrons can raise into that level. But if your bands are separated, you have an insulator that doesn't conduct electricity. Did you do band theory in Gen Chem?
Totally makes sense.
So basically a metal is the kind of the limit of infinite number of orbitals combining, because you got so many atoms. So really long chains of pi bonds, like polyacetylenes, where you have like a polymer with a bunch of acetylenes, they actually conduct electricity, because you've got this really long pi system. The electrons can go back and forth freely. But that's Gen Chem, that's not relevant to here. I'm not going to ask you about band theory. I'll let Pissner do that in 470. The what? Is that the one we just did? I can do it again, I don't mind. I think we did that one before you got here, but I mean, and then product. Like that. When you have a problem like this, the way to approach it is to count carbons, try to figure out which carbon is which. So we know the nitrogen isn't going anywhere, so we can safely label that carbon 1. And then probably carbon 2 is the one that's attached to oxygen in both cases. So what that tells us that the reaction is happening at carbon 2. This oxygen is this oxygen, because that's the one that's attached to here, carbon 1. If I number them with primes, so this was carbon 1 prime, 2 prime, 3 prime. So there's no change in the substitution pattern in the left-hand ring. We've got an oxygen attached to carbon 1 prime, a sulfur attached to carbon 2 prime, and a methyl group attached to carbon 4 prime, but there is a change here where it's a different oxygen attached to carbon 2. There's a nitro group here, and when you have a nitro group in an ortho position, you can do an ipso substitution. So you have to recognize that this is an ipso substitution or a nucleophilic aromatic substitution. Ipso substitution and nucleophilic aromatic substitution mean the same thing. So this negatively charged oxygen is going to attack that. And in this time, I actually drew the bonds in the opposite places, so I don't have to show as many arrows. When I went over it the first time, I drew the other resonance structure for the benzene ring, so we had electrons flowing all the way around the ring. But it doesn't matter, you can use either resonance form. And that is actually something to keep in mind. If you don't like where the double bonds are in the ring for the mechanism you're trying to show, move them. Right? So if you're trying to show a benzyne intermediate, and you have something that's drawn like this, and you want to make a double bond here, just move these double bonds, and then you can do the benzyne intermediate directly. So these two oxygens are both attached to the same carbon. And we have our double bond for the nitrogen. So we've broken the aromaticity of the ring. We want to regenerate the aromaticity, so we're going to come back in here and push out that leaving group. And since this is resonance stabilized, and you can draw a resonance structure that looks like this. It doesn't do anything to the ring, right? The aromatic ring stays aromatic, and this one is not. The only way to write resonance structures for that is by breaking the aromaticity of the left-hand ring, so that's less favorable. The phenoxide ion is less stable than the sulfonate ion. So it's actually just a two-step mechanism. Nucleophilic attack, and then loss of leaving group. And it's one of the chapter exercises from chapter 22. I've forgotten which one. 2212 maybe? Is that the one? I think it came right out of the book. I know it came right out of the book.
22.9, and it was page 96.
Yeah, it's only worth 8 points, so it can't be a huge number of steps. Many times mechanisms are worth 2 points a step, but in this case it was basically 4 points for the mechanism and 4 points for explaining why this is a more stable ion.
Can we go over the synthesis for the page 3?
Yes. But I'm going to save this video and then I'm going to go run and get some chalk that's not so damp.